Let us now study how a galvanometer is converted into a ammeter. Okay, so a galvanometer is converted into an ammeter by connecting a low resistance in parallel with the galvanometer. Okay, so we have galvanometer drawn here. Okay, G is the symbol of galvanometer, and then we have to connect a low resistance in parallel like this way. Okay, so we connect a low resistance in parallel. This low resistance we also call it as shunt resistance. Yes. Okay, so S means what? This means the shunt resistance. The shunt resistance we say it is S. Okay, so let the resistance of the galvanometer be Rg and shunt resistance is S. That we'll study a little later. Okay, so what happens when you send a current here I into it? Okay, the current will divide here. Okay, there's a branch here now. It will divide. Okay, the current through galvanometer we say it as Ig. That's the current through galvanometer, and this remaining current here will be I minus Ig. Okay, that current will go here. So that current will come here again, and these two currents will meet, and again we get the same current here I. Okay, so that is clear. Okay. Now if you see, this ammeter means what? This full portion. Okay, this full portion is the ammeter. The galvanometer and the shunt resistance is called as the ammeter. Okay, notice that the shunt resistance is connected in parallel to the galvanometer. Okay, now let's see some things about this. Okay, so let Ig be the current through galvanometer. Okay, it is the current through the galvanometer. Current through the galvanometer. Then S is a shunt resistance. And then we also have this galvanometer resistance now. That we write as Rg. Rg means the galvanometer resistance, or resistance of the galvanometer. Okay, galvanometer resistance. These things we must know first. Okay, what each term means. Okay, now what we must do, we must find what shunt resistance we must use. Okay, so that we can find the current there. Then next one, this current through galvanometer is a no. Okay, when the this current is a special current here, so when you give this current, what happens? The galvanometer show full deflection. Okay, so current through the galvanometer, okay, which produces full deflection. Full deflection in the galvanometer. So what does this mean? Okay, so we have a galvanometer like this way. Okay, so we're reading the dial is marked like this way. This is a pointer here, and when you send this current Ig, what happens is the needle will turn this full direction here. Okay, so you'll get a full deflection. You already learned about this ammeter, voltmeter in your 10th standard. Okay, so this one, the ammeter will turn fully. Okay, full deflection. That current is called as the Ig. Okay, now let me erase these things, and we'll go to the derivation part, how to get the shunt resistance and how to find the Ig current. Now let us try to find the shunt resistance. Okay, what shunt resistance you must keep in the ammeter. Okay, so let's see this now. We can see that when you give a voltage across this galvanometer, the same voltage will be across this shunt resistance also. Okay, so we can say that the voltage across the galvanometer, okay, will be equal to voltage across the shunt resistance. Okay, so what's the voltage across the galvanometer? We're using Ohm's law. V is equal to IR. Okay, so here I is this one, Ig, and then Rg. Okay, so V is equal to IR. That Ohm's law formula I used here. Okay, I've used here. So then shunt resistance formula. Okay, so again use the Ohm's law formula. That is I into, or this quantity into S. Okay, I minus Ig into S. So you must find the shunt resistance. Very easy. Bring this down. So what you have is Ig into Rg by I minus Ig, that's equal to the shunt resistance S here. Okay, so we can write it down separately. S is equal to this quantity I will write here again, I minus Ig, sorry, I into Rg. Okay, I into Rg divided by this I minus Ig. Okay, so this term is very easy to get the shunt resistance here in this way. Okay, now we saw how to find the shunt resistance. Okay, let's now see what will be the how to find the Ig, the current through the galvanometer. Okay, so let's see this now. So again I'll take this equation here again. Okay, so take this equation, that's Ig into Rg, that's equal to I minus Ig into S. Okay, we can take a short here. So in this equation, what is Ig? Okay, you must find. So multiply this S inside. Okay, S inside here. So we get here Ig into Rg is equal to I into S minus Ig into S. Okay. Now what you must do, you must find this Ig only now. So I take this Ig into S, this term I'll take to left side. So what happens is we get here Ig Rg plus Ig into S, that's equal to I into S. Okay. Now what's common here? Ig is common. So Ig into Rg plus S is equal to I into S. Now you must find Ig. So bring this Rg plus S down. So get here Ig is equal to I into S divided by Rg plus S. Okay. So in this way you can find the current through the galvanometer that produces maximum deflection. Okay. So what does this terms mean? Ig means the current through the galvanometer which produces maximum deflection. I is the current here through outside circuit. Then S is the shunt resistance. Rg is the resistance of the galvanometer. S is the shunt resistance. Okay. So it's very easy to find the shunt resistance and to find the current through the galvanometer. It's a simple thing only. Okay. So let me erase these things and we'll go to next topics here. So let us see the next concept here. They say that deflection is directly proportional to the current through the galvanometer. So more is the current going to the galvanometer, more will be the deflection. Okay, let's write this in a symbolic way. So deflection is said by theta is proportional to the current through galvanometer. We say it's Ig. Okay, so remove the proportional sign, put equal to sign constant. So get here theta is equal to 1 by G into Ig. Okay, so 1 by G means this is a galvanometer constant or a galvanometer resistance here. Okay, then you can also say that the current or the deflection theta is proportional to the current here. Okay, that means more is the current, more will be the deflection. Okay, so it works as an ammeter. Now we'll see how to find the resistance of the ammeter. Okay, so resistance of the ammeter we write as Ra. Ra means what? The resistance of the ammeter. Okay, resistance of the ammeter. Let's see how to find this now. Okay, so you can see this galvanometer and the shunt resistance are in parallel. Okay, so we'll use the resistance in parallel formula, that is 1 by Rg. Okay, or effective we say the total resistance is equal to 1 by Rg, the resistance of the galvanometer, plus 1 by the shunt resistance, that is S. Okay, so you must find this R effective. Okay, so what to take LCM here? So 1 by R effective on left side is equal to multiply this Rg into S, cross multiply with S plus Rg. Okay, so what done is I just cross multiply the strings upwards here. Okay, now you must find R effective, so take reciprocal. So when you take reciprocal, you get R effective is equal to Rg into S divided by S plus Rg. Okay, you can also write Rg plus S also. Okay, so this will be the resistance of the ammeter. Okay, so and one more thing you must know that the resistance of the ammeter is small. Okay, the resistance of the ammeter is very small. Okay. Why? Because ammeter must take less current to work. Okay, it should not change the readings, sir. That's one thing. Now we'll learn some more concepts about this thing. Let us now study the percentage error in the measurement of current. Okay, so I ideal, that means the current, okay, measured by the ideal ammeter. Okay, so ideal ammeter is some device, okay, which will measure the exact current. Okay, it is theoretical only. Next one is I actual current in the circuit. Okay, so I outside, this is the actual current in the circuit. Okay, so let's see the percentage error. That's delta I by I into 100% is equal to I ideal, the current ideal, minus the current actual by the I ideal. Okay, so into 100%. So this is the formula to find the percentage error. Next we will see some key points about this conversion. Okay, so ammeter has low resistance. Okay, ammeter has very low resistance. Always the ammeter is connected in series. Okay, that means one after the other. Okay, then ideal ammeter has zero resistance. Okay, so ammeter will have zero resistance. That means all the current coming in will be going out also. Okay, there is no resistance there. Then next one, see, we want to increase the current range. Okay, see, we want to measure say from 1 ampere. The reading was 0 to 1 ampere. Okay, let's imagine that we have two things here. Okay, so this is a scale of the ammeter. So this is 0 and then 1 was there. Now you want to increase the range to 5 amperes. Okay, so what you must do? You must use the shunt resistance now. So shunt resistance S is equal to Rg by N minus 1. Okay, where N is equal to 1, 2, 3, 4. Okay, so in this way we can find the, or you can increase the range of the ammeter. Okay, and they say ideal ammeter is contained series now, and ammeter is contained series. That means what? If you see any circuit here, Okay, and let's take a circuit like this way. So a battery, a bulb is there, and then we have to connect the ammeter in series like this way. So this is a series connection, minus, and this is plus. This connection is series, that is one after the. So this is a series connection. Okay. So thank you for watching.